This go. So I've done this talk a few times before, but it's probably useful for some people for a bit of revision and for new people wondering about telescopes. So the first type I'm going to talk about is called a refractor, which is what the general public, if they think of a telescope, it's going to be a refractor. Basically a lens and a tube with an eyepiece down the other end. So refractors were the first type of telescope invented. Does anyone know who invented these telescopes? Yeah, it was definitely appears to have been a Dutchman, but it's disputed over who the inventor was. It's often ascribed to a spectacle maker called Hans Lippershey, but when he put in his patent, there was a big legal dispute over it because the other spectacle maker claimed that it was prior art, that he had invented it first. So we don't really know for sure, but generally Hans Lippershey gets the credit. Then Galileo made it famous, I guess, because he learned about this invention and was the first person to systematically study the stars using a telescope and report his findings, which had a major impact on the history of science and astronomy. It's over 400 years ago now, early 1600s. So the type of telescope that was first invented had an objective lens like this, but you can see there the lines are showing the ray tracing of particular colours of light, and what you can see there where they cross is at different places. So that's what's called chromatic aberration, and there's a bit of a problem with that. You can partially get rid of it by making the focal length a lot longer, so you don't have such a steep a curve on the lens, but there's limitations for it. So you can have a really long telescope to try and get around it, but it's going to be a bit unwieldy. So this colour separation is called dispersion, and basically all optical glasses have it to varying degrees. There's some glasses that have things like, well, not really a glass, but calcium fluoride in particular has a really unusual dispersion, and it turns out that that's really useful for telescopes and similar artificial materials. But anyway, dispersion, you might think, well, it's an annoyance for telescope, but it actually was really useful for Sir Isaac Newton because he was able to use this effect in a prism to study the nature of light. So he figured out that white light is actually a mixture of different colours, and that the colours can be recombined to recreate white light. So that was one of the first sort of scientific understandings of light and an explanation of the rainbow even. And John Keats wasn't happy about this. He wrote this poem where he was unhappy about cold philosophy clipping an angel's wings, conquer all mysteries by rule and line, and unweave a rainbow. You may have heard that statement because I think Richard Dawkins wrote a book with that title. But I think Keats was wrong, really. I think it's amazing to be able to gain an understanding of the nature of light. He seemed to prefer that it was a mystery. Anyway, we come to something practical. Galileo and Kepler and the early astronomers had to put up with these single lens telescopes that had pretty terrible chromatic aberration, and they made them longer and longer to try and eliminate the effect, but you can't really eliminate it, it just reduces it. So the Dollins came up with this scheme of using two different kinds of glass with different refractive indices. I didn't mention refraction, which a refracting telescope is named after, as well as dispersion. There's a phenomenon of diffraction which causes the light ray to deflect, and the dispersion is that different colours deflect at a different angle. So making use of two different kinds of glass, they could bring at least two of the colours to the same focus. Typically, this type of refractor, which you can still buy today, they tend to be the more inexpensive ones, and they're known when you're looking at bright objects. You'll see a purple, sort of blue-purple fringe around bright objects, and that's what's causing it, because although this is showing different colours being focused, because the designer can choose which colours to bring together. Generally, for visual telescopes, they would have red and green at a common focus and the blue a bit out of focus. So if you buy it's called an achromatic refractor, you will get a bit of a purple bluish haze around bright objects because the blue and purple is slightly out of focus compared to the other colours. Okay. But that said, you can get really good optics from this achromatic design. If you want to spend a bit more money, you can get a lens that brings all colours to the same focus. It's called an apochromatic lens. And these will, to do this, they have to use glasses that have unusual dispersion properties. And one of the things I mentioned before is calcium fluorite. Occasionally that's still used, but more commonly they use some kind of artificial low dispersion, extra low dispersion glass, such as this one mentioned here, Ohara FPL 53. Ohara is the name of the company. It's a Japanese company, not Irish, in case you were wondering. Anyway, so if you these tend to be more expensive because they're using more exotic glass type, and also you've got an extra two surfaces that require polishing, and probably these days having to be coated with anti-reflective coatings. So, which I think if you're happy with refractors, you can get really nice achromat at a reasonable price. Or if you're a perfectionist and you want to get rid of the violet halo, you can spend a bit more and get an apochromatic, or APO as they're often called. Going back, say, 20 years, APO lenses were really, really expensive. But nowadays, there's manufacturers like Stellarvue, Williams Optics, and various others that are mass producing apochromatic lenses. So they are a lot cheaper than they used to be. Maybe not top quality, but you'll still get a better view than an achromat. Okay, so just a quick one. These diagrams look pretty complicated. With a telescope for visual use, the telescope itself you can't do much with. What you need is an eyepiece to inspect the image. So historically there's two schemes. You had the original Galilean scheme, as it's called, where you notice the eyepiece is actually a negative lens, and this gave an image the right way up. But the problem is that it also gave you a very narrow field of view. So Kepler came up with the idea of using a positive lens. So in other words, convex on at least one face, and this gave you a wider field of view. And in fact, pretty much all eyepieces are like that, But we still use negative lenses for specific purposes, such as a Barlow lens, which you may have heard of. It basically increases the effective focal length of your telescope. So you may want to use that for observing planets, for example. So you combine a negative and a positive lens in that case. Modern eyepiece designs are much more complex. Some of them typically would have 3, 4, or even maybe 6 or 7 glass elements in them. And generally the price goes up concurrently. The other thing is the focuser that's used is there's 2 standard sizes, and although we measure apertures of telescopes in millimeters, focal lengths in millimeters these days, we still measure the barrel size of the eyepiece as an imperial. It's just stuck. So you have the probably some of the older department store type scopes, and also some of the early Questars use this 0.965 of an inch. It's pretty rare these days that you're unlikely to come across it. Most instruments will now come with a focuser that supports both 1.25 and 2-inch eyepieces. Basically, they're a 2-inch focuser, but you have a step-down adapter, so you can fit a 1.25-inch eyepiece into the focuser. So that's basically all you need to know. There's different types. There's the old-fashioned sort of like Pirates draw tube one you've probably seen on Pirates of the Caribbean or something. We don't use that in astronomy. The more common ones are either rack and pinion focuser or the Crayford type. Occasionally you see these, I forget what they're called, a helical focuser. Sometimes come across those as well. They're just using a different mechanics to basically move the eyepiece in and out. So focuses can be quite important, especially you want one that's pretty strong. If you want to put a heavy eyepiece on there, you don't want it flopping around, or a camera especially, and then you're starting to put a lot of weight on the end of your telescope. So the focuser needs to be well engineered. You can get really cheap and nasty ones on department store scopes, and stay away from that kind of thing. Usually, in most telescopes, the focuser operates by changing the difference between the objective and the eyepiece. There is, and it moves the eyepiece usually. The Schmidt-Cassegrains are a bit different, where the focuser actually moves the main mirror. That's kind of unique to that type of telescope. And Schmidt-Cassegrains, or SCTs, are really popular with amateurs, so you're likely to encounter that. It is possible to not do that and basically lock the main mirror into position where you want it, and then focus via the eyepiece or moving your camera around. I think that's what you do, isn't it, Grant? You have the mirror locked on your SCT. Okay. Right, we come to the other main type of telescopes. We looked at, or another one, we looked at refractors, now the reflecting telescope. So this was invented by Sir Isaac Newton, who realised that where you could use lenses to focus light, you could also do it with a curved mirror. And this is probably the simplest design you could come up with: a single mirror, curved, and then one flat mirror to basically deflect the light out through the focuser tube to the side. So it's really common amateur. This is amateur scope. Dobsonian style telescopes use this scheme. So you will have, it's going from probably down to 4.5-inch size, mainly up to there's some crazy American amateurs who built these things up to a 40-inch or mirror where you have to stand on a high ladder to look through the eyepiece. It is possible, though, that you see the secondary mirror there is more or less aimed at right angles to the focuser. There are some designs where they angle it slightly differently, where the focuser, instead of being at right angles, can be closer to the primary but at an angle. So you don't have to stand so high to look through the eyepiece. And there are some designed that way. The reason you hear about the term Dobsonian is really named after John Dobson, the sidewalk astronomer of San Francisco. And he popularised the Newtonian telescope on a really simple rocker box. So you could move it up and down in altitude and spin it around. And he didn't invent it or anything, but because he made it really popular with amateurs, that scheme became known as a Dobsonian in his honour. So how do they work? Well, it's using a really simple property of mirrors that the angle of incidence is equal to the angle of reflection. So you can use this by curving the mirror to bring the light to a focus. The big advantage over a refractor with this idea is that it doesn't matter what colour the light is. This rule is the same for all the colours. So you don't have to worry about purple fringing on your images with a reflector. Okay, some of the earliest ones, I think Newton's one had a spherical main mirror. And the problem with this is that the light rays hitting the outer part of the mirror don't come to exactly the same focus as the ones that are closer to the axis. And this is a thing called spherical aberration. And that means that when you look at the image, it'll look a bit fuzzy. So you can get around this again by using a longer focal length relative to the size of the mirror. But then the telescope again becomes unwieldy, I should say. So the way you deal with this is to shape the mirror into a parabolic surface. And if you do the ray tracing, you find that all the rays, no matter where, parallel rays from a distance, no matter where they hit the mirror, they all come to exactly the same focus point. So there's still an issue that if the focus point, you're looking at a focus point that is off the axis, in other words, because an image we're looking at isn't just right in the middle, we've got images off to the side of the middle. So a parabola doesn't bring those points into exact focus. You get an error called coma, which you see in the outer parts of the images, and the faster the focal ratio of the mirror, the more coma you will see. It's possible to correct it using a sub-aperture coma corrector. When you've got a telescope that's say f6 or longer, generally you don't worry about it visually anyway, you don't really notice it. But some of these really fast, like a f3 or f4 mirror, you'll definitely see the coma in the outer parts of the field. So great right on the centre of the image, but as you get out to the edges, the coma causes the image to become a bit blurry. With a coma corrector, you can get really great photographs. I don't know if you've seen any of Rolf Olsen's astrophotography. His telescope is a home-built Newtonian with but he uses a coma corrector, and it gives absolutely superb images. Okay, we talked a bit about aberrations. So this is just to spell it out a bit more. You can see the case of spherical aberration there, where even light of the same colour focuses at slightly different places depending on what part of the lens it came through. So a good telescope will correct for spherical aberration. And we have this showing where the rays are not parallel to the axis, so coming in at an angle, forming the image. You can see the effect of coma, where the instead of getting a nice little point, the image of the point is elongated. So these are things to look out for when you're evaluating telescopes. Okay.
Would you suggest that another potential con with a reflector being the need to collimate?
Yeah, it's a learning process, I would say. Basically, people who own them and do it all the time, you don't consider it a bugbear usually. Generally, if you're throwing your telescope in the car and taking it places, you probably will have to do that. If you're just moving it in and out of a shed or something, you probably find you can go for quite a long time without doing it. But there's various techniques with lasers and so on that make it relatively straightforward. You can do it in a few minutes. It does depend on the focal ratio. If an f6 telescope is a lot easier to collimate than an f4 because the f6 is more forgiving. So yeah, if you want to get a fast, any kind of fast reflector, collimation is likely to be more an issue than with a slower focal ratio. Okay, this one is another type of reflector named after its inventor, the Cassegrain. So we have a parabolic primary mirror at the bottom there, and usually the secondary is a hyperbolic shape, and the focal point is actually behind the mirror, so the main mirror has a hole in the middle of it. This type of telescope, we have one in the observatory here up in the main dome, is a Zeiss Cassegrain. So it gives very nice images. It does have a little bit of off-axis aberration, but it's not really an issue with it. In fact, when you get nights of good seeing here, you can get amazing views through that telescope. And once it's cooled down, because it's got a really big chunk of glass, and if it's a warm day, the glass is actually giving off basically roiling warm air coming off it as it gets rid of the heat. So it takes a while for that chunk of glass to cool down. A lot of professional scopes use this as the basic configuration, if you like, but if you have a hyperbolic primary mirror, then that gives a really good corrected field. They're quite hard. Those are quite hard to collimate. It's called a Ritchie-Chrétien, and most of the big scopes use that design, like the Keck telescopes. Pretty much all of the big ones. Difference is the new Vera Rubin Observatory scope. That's a totally bizarre design. It's never been used in any other telescope. It was specifically designed for getting incredibly wide fields out of a. I think it's an 8-inch mirror with. I think the camera is something like 6 gigapixels, so it has a really large field of view. And to do that, they had to design special optics for it. Be interesting to see what that telescope produces, because it's going to image the entire sky visible from a site in Chile about every 3 or 4 nights, down to magnitude 24. So it's pretty crazy. Okay, and the last type of telescopes I wanted to mention are what are called catadioptric telescopes. Some people call them CATs. And so they're a hybrid optical system where they use both refraction and reflection. And the two common types, or not so common these days in the case of Maxitov, the amateurs come across are the Schmidt-Cassegrain. Mead and Celestron are the big players in that area. The Mead have the Alex 200 series of telescopes, and Celestron basically the main competitor in this field. And the Maxitov telescopes were quite popular for quite a long time. We've actually got a big one stored in the storeroom back there. It's a 12-inch mirror. It's really large for a Maxitov, but it really is an observatory class telescope. So if anyone has an observatory that they'd like to set that telescope up in, it's pretty big and heavy. One of the issues with Maxitovs is they have, as well as the big primary chunk of glass, the secondary is also a really big, thick chunk of glass. It has a meniscus lens, and the meniscus lens acts not only as a corrector, but it also has centre spotted as the secondary mirror on the surface of the lens. So the design is quite clever. So the secondary mirror is the same shape as the inside of the meniscus lens. Gives very good planetary images. So just a closer look at the Schmidt-Cassegrain. You have a corrector plate, which is the fairly thin piece of glass, and bolted in the middle of that is the secondary mirror. And generally, the way you collimate these telescopes is that there will be 3 screws in the secondary mirror housing that can be adjusted to basically collimate the telescope. Newtonians you collimate by adjusting the primary as well. You do have to adjust the secondary to make sure that it's properly aligned with the focuser and centered. But with these, the collimation is entirely done by adjusting the secondary mirror. And this is just showing a diagram of the Maxitov design. So again, it's a type of Cassegrain general layout, but the corrector is quite a hefty meniscus lens as shown there.
You still get diffraction spikes with the Maxitov, especially with the
No, you don't actually, because you don't with a Schmidt-Cassegrain either, because the diffraction spikes in a Newtonian actually caused by the secondary mirror holders. They're usually 4 holders, like 4 vanes that hold the secondary mirror in place. So when you're looking at images, especially, you'll notice there's diffraction spikes caused by those vanes. Some people like them. In fact, I know there's refractor owners who actually deliberately put wires across the front of the objective lens so they get diffraction spikes. Sorry, Grant?
Yeah, probably the corrector plate surfaces are also spherical. The whole point of the Maxitov is that everything is spherical, which is easy to make a machine.
Yeah, so
You need a pretty thick piece of glass to carve out the curvature of the
yeah, that wasn't mentioned in this diagram. It's basically all spherical surfaces, but the design is really clever, and it actually you get rid of pretty much all the aberrations you might be worried about using entirely spherical surfaces.
Maxitov made by Scarlett.
Oh, they still have them, yeah. I know a few years ago Mead had the ETX line that had a tabletop telescope that was really a Maxitov. I don't know if those are still around. I haven't checked their website lately. What's happened to my pointer? There he is. There he is. Okay, just a couple of things about eyepieces. A really common eyepiece design that amateurs will use is called the plossel, which is basically two doublets arranged like this. So they give quite a decent field of view of about maybe 56 degrees, something like that, and quite nice image quality. And then there's another design there which is also has 4 glass elements called an orthoscopic lens. A lot of people who obsess over really accurate geometric images because the orthoscopic has very little distortion. You know about distortion in images where you can have barrel distortion, pin cushion distortion. People who do photography are probably familiar with it. So that's the orthoscopic. And then we get to more advanced wide-angle designs of eyepieces. So what we mean by the wide angle is that it's the angle that to your eye it looks, you know, your eye thinks it's got an angle of whatever the eyepiece design is. Like if you look through a drain pipe or whatever, you've got a really narrow angle of view. And some of the cheaper eyepiece designs like Kellner's that used to be around, they give you quite a narrow field of view. Plossel is sort of an intermediate one. I know GSO have a range of eyepiece called Super Views. Not exactly sure of the design, but it gives you about I think it's 68 degrees field. Yeah. So I find that's quite a comfortable field of view to look through. But these more expensive ones, there's various different brands. The 2 shown here are made by Teleview. They're pretty expensive. Like one of these lenses costs more than a Dobsonian sort of 8 or 10 inch telescope just for the eyepiece. So the one below is one of the newer designs that gives a 100-degree apparent field of view. And you can see why it's expensive. There's an awful lot of glass elements in there. Okay, thing about Barlow lenses, when we use those, these can be useful if your telescope hasn't got a very long focal length for looking at planets. You can increase the magnification by using a shorter and shorter focal length eyepiece, but generally short focal length eyepieces also have very little eye relief. What that means, you have to stick your eye really close to the lens, and it's quite uncomfortable to use. So you might be better off using a Barlow lens. Common thing is to basically 2 times Barlow, double the effective focal length. You can get different designs. Some are more expensive than others, but quite handy. I find that one of the useful things is that you can crank up the magnification without reducing the eye relief. Especially important if you need eyeglasses to observe. If you have astigmatism and the telescope can't correct for that. Okay, so we come to a few definitions. So when it comes to telescopes, we have this symbol capital D, which represents the aperture size of the telescope or the primary mirror. So what do you think would be the effect of having a larger size for D? Sorry? Yeah, that's one of the things, you get more light. But what isn't maybe so obvious that it also increases the resolution. And that's what that little formula there, don't worry about it too much, but it's basically saying that the bigger the D is the smaller that quantity gets because you're dividing by D, and that's basically the smallest angular size that you can resolve. So as D gets bigger, that angle gets smaller and smaller, you can resolve smaller things. Unfortunately, for us here on Earth, we reach a practical limit, and that's because of the atmosphere. So you eventually run out of that benefit because the seeing of the atmosphere jumping around, I mean, in Auckland on a really good night, you might get down to 1 arc second, but your telescope might have a theoretical resolution of maybe half an arc second or better. Just one thing to point out, you notice that value lambda in there is the wavelength of the light. So the shorter the wavelength is, the better the resolution. So blue light will give you slightly better resolution than red light, or infrared, for example. Not that that really matters to us. Okay, the next thing is this letter F, capital F, is the focal ratio. So that is the ratio of the focal length to the diameter. So if you divide the focal length of the telescope by the diameter of the aperture, that's your focal ratio. So the bigger the focal length, the bigger the focal ratio. So, but generally, the longer the tube is, unless you're using optical trickery like Barlow's, that change the effective focal length without increasing the length of the tube. Okay, we have FT there is this focal length of the telescope, and then FE is another focal length for the eyepiece. So eyepieces come in different focal lengths. It'll normally be stamped on them what it is. Short focal length might be a 5mm one, and long focal length that you'd use for wide angle, maybe 30mm. And everything here is we're measuring using metric millimeters usually. And then we have the apparent field of view, AFOV, that I mentioned before. And then there's the true field of view. So what the true field of view is, the actual bit of the sky that you can actually see. For example, if you're looking at the moon's about 1/2 degree in angular size. So if you're looking through a telescope and you see the moon is completely filling up the view, then that means that your combination of eyepiece and telescope is showing you 1/2 degree true field of view. We have a thing called exit pupil size, which I'll explain because that needs a bit of explaining. Also mentioned eye relief is how close does your eye need to be to the eyepiece to take in the view. And then we have M for magnification. So those are the, that's like a glossary if you like, of definitions. And then we come to some formulas. So the first one is that the, one way to put it is the focal length of a telescope is the aperture times the F ratio. Or you can turn it around and say that the F ratio is the focal length divided by the aperture. But just an example, a common telescope in Astron's 200mm f6 Dobsonian, apply the formula and you find its focal length is 1200mm. And we've now got a formula for magnification here, which to work that out, you take the focal length of the telescope, divide by the focal length of the eyepiece. So the shorter or the lower the focal length of the eyepiece, the more magnification you get. So the example here, same telescope, we have a 25mm eyepiece, we got 1200 from the previous calculation, divide it by 25. So this particular telescope with a 25mm eyepiece, you've got a magnification of 48 times. So if you want to know the magnification, you just you need to know your aperture of your telescope and its focal length, and you basically read the focal length of the eyepiece off the barrel and you can do the calculation. Okay. So this one is a little bit more complicated. There's a relationship between the true field of view and the apparent field of view. So if you're given an eyepiece of, say, of a known apparent field of view will be quoted by the manufacturer, and you know you've calculated your magnification, you can calculate the true field of view. You just divide the apparent field of view by the magnification. It gives an example here with the same eyepiece, a 25mm Plössl, and let's say the quoted apparent field of view is 50 degrees. Then with that eyepiece telescope combo, the true field of view will be just a little bit greater than 1 degree. If you don't trust the formula, you could also measure it. You can have your telescope so that it's not tracking. Aim it, say, near the celestial equator, and then pick on a star and time how long it takes for the star to cross your field of view. And then there's a pretty simple calculation down the bottom there, basically measuring how quickly the star drifts across the field will tell you your true field of view. Not a calculation I've ever bothered to do. Okay, so the other thing that, and this is one of the important things for probably old people like me, is the exit pupil size. So, for example, the exit pupil was defined to be the focal length of the eyepiece divided by the focal ratio. So, for example, for a 30mm eyepiece divided with an f6 telescope, you get a 5mm exit pupil. So, does anyone want to guess why you'd care about that? Well, basically, when you get older like me, your pupils don't open as wide as the basic issue. So if I 5mm, I'd probably be okay. But if I had a slightly longer focal length eyepiece or a faster telescope, a lot of the light would actually not be getting into my pupil because it's not opening wide enough. So you're kind of getting a dimmer view than you would ideally get if you were a cat or something.
Bill, that's why marine binoculars are usually 750, because it's a ledge of the exit pupil, gives you the best view in the dark.
Oh, okay.
Having used them for a long number of years, I'm not sure that I'm prepared to actually see it.
Yeah, you can actually see the exit pupil in binoculars. You can hold them away from yourself and you'll with a bright background, and you'll actually see a circular spot, which is basically the exit pupil. Okay, we're just going to talk briefly about mounts. There are two essentially different types. The first is the alt-azimuth mount, and that's the Dobsonian mount we talked about before, where we have we rotate around the azimuth, which is your compass bearing, and we can tip it up and down in altitude. So just by turning the telescope around or tipping it up and down, we can cover the whole sky. It actually gets tricky when you're observing straight up at the zenith, because you go across it and you have to spin the thing right around. So computer-controlled alt-azimuth mounts go haywire when you cross the zenith. They'll suddenly do a really fast motion. And if you do the maths, it says you have to actually rotate at infinite speed as you cross the zenith But of course, a real motor can't do that. But it can, for practical purposes, it can make it actually quite difficult when you're working near the zenith with a Dobsonian to just keep the thing in view. So the other type is basically still two axes. You have one at 90 degrees to the other, but the difference is that one of the axes is aligned to the axis of the Earth. So if you were here in the previous talk, you saw images of star trails. Well, the trails are, the stars are effectively or apparently rotating around in the point of the sky called the celestial pole. We have one in the southern and the northern hemisphere. They have a reasonably bright star, Polaris, in the northern hemisphere near the pole. In the south, we only have a really faint, the nearest star, brightest star, about 6 magnitude, which you can't see at all from the city, close to the pole. So we have to use other methods to find the pole in the southern hemisphere. But you can see where it is in these star trail pictures, because you can see where the point in the sky that the stars are effectively rotating around. So the idea is your equatorial mount has one axis pointing at the pole, and so your rotation is around the pole, and then you tilt the other way so that you have the two axes in the equatorial mount. One of them is called your declination axis, which is basically north-south, and your other axis is called right ascension. I won't go into why it's called that, but that's another talk. But that basically tracks the stars as they're moving across the sky. And the advantage of the equatorial mount is that you can track the sky without field rotation. I don't know if I want to talk about that tonight either. But it's handy for astrophotography. You can actually convert one into the other. Meade and Celestron, the mounts for some of their scopes, which when you buy it, it comes as an alt-azimuth mount, but you can buy an accessory called a wedge, which basically just tilts the thing, and you can adjust the amount of tilt so that you can aim one of the axes at the pole, at your pole, whether you're in the northern or southern hemisphere. So with that type of mount, you've got a choice as to whether you want to operate at alt-az or equatorial just by the use of an accessory. So the advantage of alt-azimuth is that it's really cheap. You don't really... equatorial mounts can be quite tricky to get your head around if you've not used them before. Whereas people are familiar with alt-azimuth because it's sort of the way our eyes work. We just tilt up and look around. There's variations on this, and in the Smith-Cassegrain system, they use what's called a fork mount. So basically where the telescope is held on both sides. And a fork mount can operate as either an equatorial or alt-azimuth. It's just the advantage of a fork is that for engineering purposes, it gives you something that's easier to balance. And I'll show where that comes in a minute. So this one here is a type of equatorial mount called a German equatorial. And the issue here is that you have to basically have had something on the other side of the axis to balance the weight of the telescope. So that's why there's a big steel counterweight there. And if you're putting different accessories on the telescope, like cameras and so on, you may have to adjust that counterweight, either add more or less or move it in and out to to balance the telescope. So that's something you have to do with this type of mount, is that when you're setting up, you have to make sure that the telescope is balanced before you start using it, or the drive motors will complain. Oh, I've lost my pointer again. Here we go. Oh, yeah. I think, that was all I was going to talk about. I think we're all done, so we've got any questions?
Is that one of those there?
Yeah, that is a German equatorial mount right
I
there.
was going to point at that. So and that's the Alpaz mount.
Yeah, yeah.
The wooden tripod.
Yeah. So you can see that it's got the counterweight for this comes as part of a set, so it was designed with that particular counterweight in mind. A lot of the ones you buy, because they don't know what you're going to put on the mount, they'll have sets of counterweights, and you just put on whatever you need to balance the telescope. The big Zeiss telescope upstairs is a type of German equatorial as well, but it's a slight variation. We can't show you it at the moment because it's being refurbished after the dome has been replaced. It's looking beautiful, by the way. The dome, new copper and everything, looks great. Yeah, but that has a massive counterweight as well for the same reason. But the difference is that it has a pair that comes up like that one, but then it goes off at an angle that's basically designed for this latitude. And the reason for doing that is so the telescope can actually swing under the mount. So I think it's officially called as an offset German equatorial, I think is the official name. So the offset allows you to swing the telescope under the mount.
Is that the original telescope that was put here?
Yes, it was installed 1967, I think. Grant was actually here when it was installed. He was a young teenager when he joined the society. But yeah, what happened was Edith Winstone Blackwell donated the funds to buy the telescope, but for quite a long time they couldn't buy it because they didn't have anywhere to put it. So it took a number of years till they got this site, and then it was ordered from Zeiss, and the original building was built back in the mid-1960s and opened in 1967. So it has had some upgrades, like it used to be a manual push-to system, and then it would track with a tracking motor controlled by a clock mechanism. But for its 50th birthday, it got an upgrade, so it's now fully computer controlled. So you don't push it around anymore. It's got drive motors. Much heftier ones, of course, than you'd see on a typical amateur mounting system, because it's a pretty big telescope. Yeah.
How much about those new harmonic drives that have the mounts?
No, I don't.
Yeah, it's been quite interesting.
To see them advertised here for an equatorial mount
Oh,
arrangement, but you don't need a counterweight.
Yeah.
oh, okay.
Quite,
Because of the
quite
drive is able to take the weight of the telescope. I imagine there would be a limit though, to how big the telescope could be and not balanced. I guess there's going to be some fundamental engineering things once you get above a certain size.
Yeah, some of them have an option to add the counterweight.
Oh, okay. I know there's, I think Planewave have got a different drive system where they use direct drive, so there's no gears. So their motors are basically just direct driving with no gears. And so those are quite powerful motors as well. And supposedly they're very accurate, so not exactly sure how they work. Any other thoughts or questions? Things to tell us?
One thing I do know about having a Barlow lens,
Yeah.
and I learned that very early on, is that it effectively doubles the amount of eyepieces that you've got straight away.
Well, yeah, that's right. Because if you have a 10mm lens, you throw a Barlow on it, it sort of behaves like a 5mm lens if it's 2 times Barlow, yeah. So you can combine the Barlow with each of the eyepieces you own. So that is another benefit of it.
Is this the upgrade to this one? Does that allow you to take photography from it as well as it's motor driven?
You can, but it's a little bit tricky because part of the deal with the telescope, or I guess you'd call it the bequest, was that it's got to be available for use with the public. So the Stardome have, you know, you have to pay for a ticket, but you get to look through the telescope. And the problem is if it's being used for visual use, it's a real pain to take cameras off and on. You have to redo your flats if you do that. And yeah, I think, you had an idea about having some kind of a flip mirror system where you could leave the camera on there, but I don't know how.
Basically, just decide to leave it as a visual only telescope.
Right. Okay.
Maybe put a SLR or something on the back if you want to take pictures.
Yeah. People in the society here can do that on club nights. We can just take the diagonal off. That's something I didn't mention actually. I should probably bring that up. I should have added it into here. When you're using a lot of telescopes, you don't want to be looking straight up the tube. It can be very awkward if you're looking at the zenith and your eyepiece is down here. You have to crouch down on the ground. So you'll often have a diagonal mirror that basically fits into the focuser and brings the image out at a more convenient angle for viewing. So the Zeiss has one of those on it for visual observing. Smoke-Cassegrains will generally have one of those. And refractors, basically any time you're using them for visual use, just because otherwise it's really awkward to look through them if you have to sort of be down on the ground looking up like this. Yeah, but you don't need the diagonal if you're using a camera. Okay, well, thanks for coming along, and I believe it's... Film night next week. What's the